One 5G system can carry more than one logical network at the same time. So here's the puzzle. When a device connects, how does the system know which logical path this device may use? Not just whether the radio signal is strong. The harder question is permission and selection. The same physical access network can lead toward different network slices, each with its own service path. On screen, one shared system will divide into two possible lanes. The device is not choosing a lane by guesswork. It needs a controlled conversation with the network. The source separates that conversation into two linked stages. First comes registration management. Its job is to select an access and mobility management function, or AMF, that supports the slice needs. Then comes PDU session establishment. That later stage connects the device to the desired data network through one or more network slice instance. That separation matters. Registration is not the same thing as opening the final user plane connection. Registration establishes the network relationship and returns the slice choices that are allowed. A later PDU session uses those choices to reach a data network. For a concrete mental model, think of a building with one entrance and several controlled corridors. The entrance proves that you are arriving. The corridor decision determines where you are allowed to go. The first stage does not pretend to be the entire journey. It prepares the permitted routes. Watch the two lanes appear. The device needs a permitted path, not merely a radio connection. That is the problem the rest of the exchange solves. Before the device asks the network for registration, it is not starting from an empty page. It has configured slice selection information. The source calls this the configured NSSAI. The NSSAI is the set of slice selection information associated with the device. Inside it are individual S-NSSAI values, the identifiers for particular slices. The policy behind that starting information is the Network Slice Selection Policy, or NSSP. In the source diagram, the NSSP is provisioned to the UE, and the source describes it as received from the Unified Data Management Function, the UDM, via the AMF. The important idea is not a mysterious database download. It is that the device begins with guidance about which slice choices are relevant when it later makes a request. Now notice the subtle point. Configured does not mean finally allowed. A list of possibilities is not the same as a decision for this registration. The device may have slice selection information, but the network still needs to check subscription data and perform slice selection. Our routing desk metaphor makes this visible. The UE arrives with a small route card. That card tells the desk what kinds of lanes to ask about. It does not unlock every lane in the building. The card is input to the conversation, not the result of the conversation. So the starting state has three layers. The UE has a configured NSSAI, the NSSP is the policy used to provision that information, and the individual S-NSAIs identify the slice choices inside it. Keep those roles separate. The UE begins with guidance, while final permission is still ahead. The next problem is turning that starting information into a request the network can act on. The UE sends a registration request. Inside the request, it includes the requested NSSAI, the slice selection information it is asking the network to consider. Watch the packet move first from the UE to the RAN, the radio access network. The RAN is the radio side entrance to the 5G system. In the source, the RAN uses the requested NSSAI together with other criteria to select an AMF that can support the registration. The AMF is the core function that will manage the registration and mobility relationship with this UE. This is a crucial distinction. The RAN is not deciding the final subscription permission by itself. It helps select the right AMF. The requested NSSAI gives the selection process something meaningful to work with, while the other criteria are part of the network's decision context. Here is the misconception to remove now. Requested does not mean granted. Sending a preference or need into the system is not the same as receiving authorization back. The message starts the check, it does not finish it. The source also protects us from overreading the simplified picture. A security procedure is performed during registration, but it is not shown in the source diagram. We mark that gap visibly instead of inventing a protocol trace. The omission is deliberate. This lesson is following the slice selection path. By the end of this step, the request has reached the right decision-making function. The RAN has helped choose an AMF, and the AMF is now ready to check what this UE is subscribed to use. Now the AMF has a request, but it still needs evidence about the UE. The next question is simple. What does this subscription actually include? The AMF retrieves subscription data from the UDM, the Unified Data Management Function. The UDM returns data that includes the subscribed NSSAI. This is the network's record of the slice selection information associated with the subscription. It is not merely a copy of whatever the UE happened to request. Put the two cards side by side. Requested NSSAI means these are the slice choices I am asking you to consider. Subscribed NSSAI means these are the slice choices attached to the subscription. They can be compared because they play different roles. One comes from the registration request, the other comes from the network's subscription data. This comparison is the reason the UDM step exists. Without it, the network would have a request but no subscription context. With it, the AMF can reason about the relationship between what was asked for and what the subscription supports. Use the routing-desk picture again. The UE arrives with a route card. The desk now opens the account file. The card says what the visitor is asking for. The account file says what the visitor's subscription contains. The desk has not opened a lane yet. It has only gathered the two pieces needed for a responsible decision. That distinction will matter in the next scene. Subscription data is necessary, but the source shows one more function involved before the network returns allowed slice identifiers. The AMF must ask the NSSF to perform slice selection. The AMF now has two inputs, the UE's requested NSSAI and the subscription information that includes the subscribed NSSAI. The next problem is selection. Which slice choices should the network actually make available for this registration? The AMF queries the network slice selection function, or NSSF. Think of the NSSF as the routing desk that turns the collected information into a selected set of lanes. The NSSF returns two kinds of result shown in the source: NSI ID information and allowed S-NSSAIs. The allowed S-NSSAIs are the individual slice identifiers that the network permits for this UE in the current registration context. The NSI ID identifies the selected network slice instance information associated with that choice. Keep these ideas distinct. An NSI is not simply another name for the UE's request. The request is an input. The NSI information and allowed identifiers are outputs of the network's selection step. Watch the diagram change from several pale possibilities to highlighted lanes. That visual change is the causal point. The AMF did not simply repeat the request. It asked a selection function, and the selection function returned a constrained result. The word allowed is doing real work here. It tells us that the final list is produced by the network after considering the request and subscription context. We are not claiming that every configured or requested S-NSSAI automatically survives. In plain language, the permitted slice identifiers are the lanes the network is willing to open for this UE. The AMF now has the decision it needs to send the registration outcome back to the device. The selection result now has to reach the UE. The AMF sends a registration accept to the device through NAS, the non-access stratum signaling path. This is the network's answer to the registration request. The source lists important contents of that message. It includes the allowed S-NSSAI, a 5G GUTI, the registration area, and other registration information. The exact point is not to memorize a bag of fields. It is to see what the message accomplishes. It returns the network's registration decision and the slice information the UE may use. On screen, the highlighted lanes travel back across the same path, from the AMF through the RAN to the UE. The device then updates its NSSAI, including its list of allowed S-NSSAIs. The route card it carried in at the beginning has been changed by the network's decision. It now reflects the permitted slice choices for the registration. Here is another boundary that is easy to blur. Registration tells the UE which slice choices are allowed. It does not, by itself, establish the final user plane data connection. The source names that later step PDU session establishment. A PDU session connects to the desired data network through one or more network slice instance, using the slice choices that registration made available. So the journey has two linked but different moments. Registration narrows the map. A later PDU session uses an allowed route to create user plane connectivity. The first stage makes the second stage possible without pretending they are the same procedure. Let's run one compact example through the whole mechanism. Imagine a UE with a configured NSSAI containing two possible slice choices. When it sends a registration request, the requested NSSAI carries those choices to the RAN. The RAN uses the request, together with other criteria, to select an AMF. Now the AMF retrieves subscription data from the UDM. That response includes the subscribed NSSAI. So the AMF has both sides of the comparison, what the UE asked to consider and what the subscription contains. The AMF then queries the NSSF. The NSSF performs the slice selection step and returns NSI ID information plus the allowed S-NSSAI. Notice what changed. The UE did not simply repeat its original list. The network returned a selected, permitted result. The AMF carries that result back in a NAS registration accept. The UE updates its NSSAI and its list of allowed S-NSSAIs. At that point, the UE knows which logical slice choices are available for the registration. The actual user plane connection is still the later PDU session establishment step. This worked trace is useful because every arrow has a job: request, subscription check, network selection, and return. The diagram is no longer a chain of labels, it is a chain of reasons. Step back from the diagram and the whole pattern becomes clear. The UE begins with configured NSSAI information, provisioned through the network slice selection policy. It sends a registration request containing the requested NSSAI. The RAN helps select an AMF. The AMF retrieves subscription data containing the subscribed NSSAI from the UDM, and the AMF asks the NSSF for slice selection. The NSSF returns NSI ID information and allowed S-NSAPIs, and the AMF sends those registration results back in a NAS registration accept. That is a request, check, select, return pattern. The request expresses what the UE wants considered. The subscription check supplies network context. The selection step turns those inputs into permitted slice identifiers. The return message updates the UE so it knows which choices are allowed. The broader idea is policy-driven network virtualization. One physical 5G system can present multiple logical networks or slice paths without treating them as one undifferentiated route. The shared infrastructure stays in the background, while policy and selection determine which logical path is available to this device. And the boundary still matters at the end. Registration provides the allowed slice choices. Subsequent PDU session establishment creates the user plane connection to the data network. You should now be able to look at the diagram and explain every arrow as a reason, not just a label. The UE brings guidance. The network checks entitlement and selection. The AMF returns the allowed result. The next question is wider. What other decisions could the same request, check, select, return pattern coordinate in a network?